this lecture, I'll show you how to do matrix multiplication. That's a multiplication of two matrices. This is for Math 107, Chapter 5. Matrix multiplication is very complicated. It's a combination of multiplication and addition. And as I've written here, it's almost impossible to describe in words. First thing I want to point out, though, is that matrix multiplication is not commutative. If I multiply two numbers together, say 3 times 4, I get 12, and that's the same as 4 times 3. This is regular multiplication, and it is commutative. Same with addition. 3 plus 4 is the same as 4 plus 3. Addition is commutative, but matrix multiplication, which is what I've shown here, is not commutative. In fact, even if you can multiply A times B, you might not even be able to multiply B times A. It's possible that it won't be defined for B times A. The reason that multiplication is defined for certain combinations of matrices and not others is that there are requirements for matrix multiplication. These are requirements on the matrices that you're multiplying. The requirement is that the number of columns in the first matrix, that would be the matrix on the left, has to equal the number of rows in the matrix on the right. So what I mean by this, if I'm multiplying A times B, the number of columns that I have here has to equal the number of rows in the second matrix. So if I wrote the order of A as an m by n, let's say A is an m by n matrix in general, and B is an n by p matrix, then I could multiply these two together because n is the same, the number of columns in A is the same as the number of rows in B. The result will be an m by p matrix. It will have the same number of rows as the first matrix and the same number of columns as the second matrix. Let me put some numbers to that. Say I have a matrix that's 4 by 10, 4 rows, 10 columns. I can multiply any matrix now that has 10 rows. Let's say I have a 10 by 2. So I can perform this multiplication because the number of columns in the first matrix equals the number of rows in the second matrix. And the answer will have 4 rows and 2 columns. 4 came from the first matrix and the 2 columns came from the second matrix. In this case, you can see that you could not do this multiplication in the other order. In that case, you would be trying to go 10 times 2 times 4 by 10, and these two numbers are not the same, so matrix multiplication is not defined for that situation. Here's an example. You might not know how to do this at this point, but by the end of the lecture you'll know how to do this kind of multiplication. Okay, so what we have is two matrices. We could call this one A and B, just to give them names. And let's say A is, well, from this as shown here, A is a 3 by 2 matrix, 3 rows and 2 columns, and B is a 2 by 3, 2 rows, this row here and here, and 3 columns. So writing that out, I've got a 3 by 2 times a 2 by 3. These numbers are the same. I can carry out the multiplication, and the result will be a matrix with 3 rows and 3 columns. And if you look at the answer here, it is a 3 by 3 matrix. We're going to start with simple examples and then work up to more complicated ones. So here's the first example I'm going to do. It is just a the first matrix has 1 row. Whoops, I have a pen. First matrix has 1 row. The second matrix has 1 column. In this case, we have a 1 by 3, because we have the 3 columns here, and we have a 3 by 1 for the second matrix. So we can do this multiplication because these two numbers are the same. Right. So I'm going to erase that for a minute and show you how to do this. You might remember little kitty blocks. They usually, they usually look like this, and then up have kind of an outline, and maybe they got a block A in here, and then there's another one with a B, or maybe they have numbers in them. Well, usually they're all separate blocks like this, right? But sometimes they aren't, they stay stuck together, they didn't get cut. And so you might have an A and a B stuck together like that. I'm going somewhere with this. Okay, so you kind of recall that. You might have some that have 3 stuck together. That's quite unusual, but say that happens. Okay, what you do is you take that idea and you imagine that 1, 2, 3 are some kind of little kitty blocks like this, all stuck together. So here's that block here. The 1 and the 2 and the 3 are all here, and they're as a group. Then you take that block and you turn it sideways. I'm going to give myself more room here. Let's say I have the 1, 2, 3 here, and then this is my second matrix, 10, 11, and 12. So I have this matrix, I'll show it in red. I take this and I turn it sideways. Of course, I'll have to write the numbers going up to make any sense. 2, 3. And now you see that the 10 and the 1 sort of match up spatially, the 11 and the 2 are matched up, and the 12 and the 3 are matched up. You multiply the 1 times the 10, the 2 times the 11, and the 3 times the 12, and you add all the results together. And that's what's shown here. 1 times 10 plus 2 times 11 plus 3 times 12, you add all that up, and there's your answer, 68. If we looked up here, again, with 3 and 3 were the same, so the result was going to be a matrix with 1 row and 1 column. Of course, you might say that isn't even a matrix, but just for learning purposes, let's just go ahead and say this is the matrix that we get. Call it a matrix. But do you see what happened? I took the 1, 2, 3 as a group, turned it sideways, and then you can see which numbers line up, multiply those, and add the results together, and that's your answer. Now we're going to move up in complexity by saying that the first matrix has 3 rows instead of just 1. So we're taking a 3 by 3 times a 1 by 3. The number of columns in the first matrix equals the number of rows in the second matrix, so we can go ahead and do the problem. And the result will be a matrix that has 3 rows and 1 column. So how this is done is row by row, the same thing that we did on the previous slide. You take the 1, 2, 3, so it's all stuck together, turn it over, and go against that first column. This is row 1 against the first column. You're creating the first row in the answer. 1 times 10, 2 times 11, 3 times 12, add those all together, and you get the answer of 68 in this case. All right, now you're done with row 1. You move to row 2. And you do the same thing. You pretend these are all stuck together, and you go against the first column. So you'd have 4 times the 10, 5 times the 11, 6 times the 12. Maybe from this you can see how come you need the same number of columns in the first matrix as the number of rows in the second matrix. So from working with R2, row 2, you created row 2 in the answer. And now we have a third row, row 3 down here. 7, 8, 9, do the same thing. You take and go against column 1. So the 7 multiplies the 10, the 8 multiplies the 11, and the 9 multiplies the 12. You add those products together, and there's your answer. And you can see here we have a 3 by 1 matrix as expected. Now what we just did was take a 3 by 3 times a 3 by 1. And we could do that because these numbers are the same. But if we turned it around and tried to multiply the second matrix first times, the first one, we would be going 3 by 1 times a 3 by 3. But these numbers are not the same, so we couldn't even do the problem. Here's what it would look like. And it's not defined. Now here's our third example, and this is as complicated as it gets. In this case, we have several columns in the second matrix. So we're multiplying a 3 by 3 times a 3 by 2. The number of columns in the first equals the number of rows in the second, so matrix multiplication is defined for this situation. And the result would be a matrix with 3 rows and 2 columns. Here's how we do multiplication in this case. We take the 1, 2, 3 again, so this is your row 1, and we go against that first column, and you see those entries here as before. Then you're done with that column, and you take it and go against the second column. So it would be 1 times 20 plus 2 times 30 plus 3 times 40. Now you've taken row 1, you took row 1 against column 1, you created row 1, column 1 in the answer. And now you've taken row 1 against column 2, so you created this entry, which is first row, but the second column in the answer. Now you move down here and you grab the second row, and you go against the first column. So it would be 4 times 10 plus 5 times 11 plus 6 times 12. Okay, that's done. You've created row 2, column 2 in the answer. Row 2, column 1 in the answer, I'm sorry. And now you go against the second column. 4 times 20, 5 times 30, 6 times 40. You have one more row. So the final row here, R3. You take row 3, the 7, 8, 9 are all together, and they go against column 1. Okay. And this creates row 3, column 1 in your answer. Then you move over and go against the second column and create this entry here in the answer. And here's your result as expected. It's a 3 by 2. Just like the previous example, this case cannot even be done in the other order. Before we had a 3 by 3 multiplying a 3 by 2. These numbers are the same, so matrix multiplication is defined. But if we try to go in the other way, put the second matrix first, we will have a 3 by 2 times a 2 by 3, but these numbers are not equal, so matrix multiplication is not even defined for this combination. And that's what the problem would look like. You might attempt to do it that way. See what would happen? You would take this first row, 10 times 2, go against the first column, but not every. You would have a 10 times a 1, a 20 times, times a 4, but then what happens here? I'm going to give one more example. In this case, I'll take a 3 by 1 times a 1 by 3. So these numbers are the same, so I can proceed with the multiplication, and the answer will be a 3 by 3. So the first row has only one entry, 10. So I take it and I go against column 1 here. Column 1 has only one entry, 1, so that gives me my first number there, 10. Then I take row 1 and go against column 2. That would be 10 times 2. Then I take the 10 and go against column 3, which is 10 times 3, and that gives me my first row, and I'm done with that one. Now I move to the second row. In the second row I pick up just an 11, go against column 1 to get 1 times 11, go against column 2 and get 11 times 2, go against column 3 and get 11 times 3. And now we have the third row, which is row 12. Against row 1 would be 12 times 1. Going against, column 2, you'd be 12 times 2. Going against column 3 is 12 times 3, and there's my answer. There's the 3 by 3 that I expected. I want to give one more example, and in this case, I will multiply a matrix by the identity matrix. If you recall, the identity matrix is a square matrix. That means it has the same number of rows as columns. In this case, it's a 3 by 3, and all along the diagonal are 1s, however big it is, and everything else is a 0. And that's what we have here, 1s along the diagonal and 0s elsewhere. This is the identity matrix, and it's multiplying this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Now look what happens when this multiplication is carried out. I start here with the 1, 0, 0, and I go against column 1. Well, the 0 multiplies to 4, and the 0 multiplies to 7, so those don't count for anything. Well, those are zeros, and 1 times 1 is the only number I get out. Then I move over to column 2. Well, 0 times 8 is 0, 0 times 5 is 0, but we have 1 times 2, and then move over to the third one, and all you have there is 1 times 3, everything else 0. That gives me my first row in the answer, 1, 2, 3, which you see is identical to the first row in the second matrix. Now move down to the second row, 0, 1, 0. The 0 multiplies the 1, no contribution, 1 times 4, and 0 times 7. Move to the second row, second column, and you would have 0 times 2, 1 times 5, and 0 times 8. Moving to the third column, 0 times 3, 1 times 6, and 0 times 9. Working that out, you get the second row, which is identical to the second row in the matrix up here. Now moving down to the last row, 0, 0, 1. The zeros go against everything except the entry in row 3. That gives me 1 times 7. Move to the second column, first column, second column, zeros except for 1 times 8. And the third column, of course, get 1 times 9. And here's the matrix, which you see is identical to the second matrix in the problem. In symbols, that's identity matrix times any matrix A is equal to A. In fact, it works the other way too. This is one case that commutes. A times the identity matrix is A. And now you see why it's called the identity matrix. In multiplication, 1 is the identity. So if I go 3 times 1, I get 3. And here, I times A gives me the same matrix A.